Okay, for better or worse, you're about to spend about 8 minutes of your life listening to a lecture on solids, liquids, and gases. Not talking about plasmas here or anything else, just the big three, solids, liquids, and gases. So let's start with solids, one that we are familiar with. And solids, what are the particles doing? Well, the particles in a solid are locked in place. Now, before you get the idea that they can't move at all, I'm going to put the word locked in quotes here because even though the particles are locked in place, they're still shaking, they're still vibrating in different directions. So that's what a solid can be like. Now, you can imagine lots of particles, and if they organize themselves into a crystal like this, you could have like a piece of salt. If you ever look really closely at a salt crystal, it's always cubical. Or the particles can be locked together in a random looking pattern, and that's another way solids can have their particles organized. And then moving along to liquids, what are the particles doing? In a liquid, the particles are sliding around. So that's why liquids behave the way they do. The particles are still touching each other, but they can slide past each other. It's kind of hard to draw in two-dimensional notes, so I went and I borrowed this. Watch this just for just a few seconds.
So in liquid water, the water molecules not only vibrate, they can also rotate and slide past each other. And this is what allows the substance to flow. At even higher temperatures, the water molecules become free of that liquid.
Okay, so that's what the particles are doing in a liquid. They're sliding past each other, rotating, moving around. And then in a gas, what are the particles doing? Well, in a gas, the particles are flying around. They're bouncing all over the place. So I'm going to write the particles are bouncing around. So if you could see particles of a gas in a container, if they were big enough for us to see, what you would see is lots of little particles bouncing all over the place. Off of each other, off of the sides of the container, just off of everything. So that's what the particles are like in the three states. Now let's talk about going from one state to another. So if you start with a solid, you can add energy to it. And if you add energy to a solid, you can get a liquid. Or if you add energy to a solid, you can get a gas. You can also add energy to a liquid and get a gas. So all of these red arrows, these adding energy arrows, and specifically I'm talking about heat energy, but if you add heat, you eventually wind up at gas. Okay? Now, there's a word for this, adding heat. We call that word endothermic. Okay, so these processes require heat to happen. Are the opposites of these things true? Yes, they are. If you take a gas and remove energy, you can get a liquid or a solid. And if you take a liquid and remove energy, you can get a solid. So the word that describes removing energy or releasing heat energy is called exothermic. So this is making me question why I used blue for something that releases heat and red for something that absorbs, but maybe it's okay after all. Okay, let's talk about these one at a time. Let's start with something that we're probably all familiar with. Let's talk about something freezing. Think about a candle, and let's think about the candle wax after it has dribbled down. After the candle wax has dribbled down from the heat source, from the flame, what happens to it? Well, the candle wax hits something colder. It hits this, whatever this is, some kind of a stone surface or something. So the particles, what do? The particles go from being a liquid to being a solid, which means the particles have slowed down. In other words, they must have given off some energy, so they went from a liquid to a solid. And then to watch the opposite, or to see the opposite happen, what if you've got some ice cream and you take the ice cream someplace where it's warm? The heat from the area goes into the solid and it turns it into a liquid. So that's the opposite. So we've got melting here and we've got freezing here. If you're going to melt something, you have to put energy into it. That's endothermic. And if you're going to freeze something like this candle wax, you've got to take energy out of it. Okay, that's exothermic. Going from a liquid to a gas, everybody's familiar with this one. Boiling water, you can see this is a liquid, and then these little bubbles here, they are not made of air, they're actually made of water, but it has turned into a vapor, it's a gas. So if you add energy to a liquid, you can get a gas. And what if you remove energy from a gas? Can you get a liquid? Well, yes you can. That is called condensation. So if you've got a cold window, it's cold outside, the moisture in the room, the gaseous water, hits that cold window and the particles slow down, they give off their energy, and it turns into a liquid. That's called condensation. Okay? And then down on the bottom here, these bottom two arrows, I'm actually going to write the names of these two because there's a possibility you haven't heard these words before. If you take a solid and turn it directly into a gas, if you add energy to it, that is called sublimation. Too big of a pencil here. How about this? That's called sublimation. What's sublimation? An example of sublimation is, how about this? On a sidewalk, on a cold, icy sidewalk, as the day progresses, some of that ice is just going to disappear. And without melting, it'll just disappear. It'll be gone. That happens pretty slowly, so people don't really notice it much. One example of sublimation that happens a lot faster is with dry ice. That's solid CO2. The particles don't like each other very much, so they're constantly jumping off and becoming a gas. That's something it's kind of cool to watch, actually. So that's called sublimation. And what if you go from what if you go in the opposite direction? What if you go from a gas to a solid? We call that deposition. Think about just the first word here, deposit, putting something down. Okay, so deposition, an example of that would be snowflakes forming. Up in the air, you've got gaseous water, which is invisible, and when it gives off heat, if it happens rapidly enough, what happens is you can go directly to a solid, and you get snowflakes. One more example of deposition happening is frost. You've all seen frost before. You go out in the yard and the grass is white one morning and it didn't snow. Why? Because the water vapor from the air cooled off, and when the particles cooled off, they gave away their energy and they slowed down, and you got a solid. So you got all these little ice crystals on the grass. Okay, I really don't want to go over 8 minutes, but there's one thing I really need to cover, and that is that kids often get confused by the environment and the process. Let me explain with this example. Have you ever put your hand behind a refrigerator while it's running? There's these coils in the back, and the back of the refrigerator gets hot. So keep that in mind. Now let's talk about a liquid. Let's talk about a glass of water. You're going to take a glass of water and you're going to stick it in a freezer or a refrigerator. What does that do? Well, the liquid turns into a solid if you're going to freeze it, right? So if you're going to go from a liquid with the particles moving more to a solid with the particles moving less, that means that you had to do what? You had to give off heat, okay? So that is an exothermic process. So it had to give off heat. So that means when you go from a liquid to a solid, the environment actually gets warmer because it's giving off heat. And the proof of that is the coils on the back of the refrigerator. So a lot of kids think, well, in a fridge it's cold, so that must be endothermic. Well, no, the liquid is giving off heat. Okay, so that's why it's exothermic. That's probably going to get a quiz question or two right for you if you can